have infinite energy in the ground state or the vacuum state, do not call it ground state, this is vacuum state. Okay. So, that will come in the next slide, just give me 1 minute. So, this space with number of particles, this is not like Hilbert space, right. Hilbert space for an operator linear, in fact Hilbert space is mathematical construction, okay. It is not well, quantum mechanics borrowed it from Hilbert, from the mathematicians, but given operator L, linear operator L, we can define Hilbert space based on the eigenstates for operator L, right. I mean this is formalism. Now Hilbert space for oscillator, we have ground state, state 1, state 2 and like that, but now we got lots of oscillators. So, we have in fact bigger space than Hilbert space, right. In fact, it is kind of direct product you can think of, okay, of many Hilbert spaces. So, this is called Fock space, this is a Russian physicist or mathematician, I mean. So, Fock space is a direct sum of tensor products of Hilbert spaces for each particle number. So, this is taken from Wikipedia, and the state psi is a basically is in a Fock space, okay, and this Hamiltonian which I wrote in the last slide. So, nk particles with energy omega k living in that wave number k, okay, and this is my state for the field. So, you can think of space where whether you can't really think of real space, this is not in real space, this is some abstract space where there are particles. Let me make this remark, when we do the experiment or any of the calculations, we will assume that this is abstract space, okay, abstract space, and there are particles in there. So, we send one particle, okay, this particle goes in, interacts inside and comes out. Well, maybe same particle will not come out, some particle will come out. So, it will have some signature of what is there inside. We cannot look at all of it, it is impossible. So, this is scattering, okay. So, we are basically in a collider, we are sending one electron, it does something and something comes out, from that we are trying to deduce what is there inside that state, okay. So, this is the formalism. In fact, we send in one particle or we can send several particles and something comes out, and from that we deduce what is there in that state, okay. So, yeah, that is how we calculate, that is a normal procedure for this. And in field theory we do not work with multi-particle wave function, okay, because the particle numbers are changing, is simply impractical. So, vacuum energy. So, as I said, this integral is infinite, right, this straightforward, nothing complicated. So, if you have infinity, then what do we do? So, one thing is to say, well, there is infinity, but we will keep that as a background, and anything above that infinity is what we will measure. So, that is what is we compute. So, we compute this, okay. So, infinity part is kept aside, in fact that leads to a lot of mathematical intricacies called Wick's theorem and so on, how to make sure that the infinity is not coming in your calculation, okay. So, we measure something which is on top of that infinity, and that is what is our energy, and this is our energy without half. Okay, so that is about what I wanted to say about the second quantization for bosons. Okay, so I think let it be on. Let us see some interesting questions. We can keep it recorded.
Is it finite?
This one will be finite. This will be finite. But well, I mean again, yeah. So this will be finite. What we can say the psi, the state I said, with n1, n2, n3 like that. This is the eigenstate of Hamiltonian. Okay, so you are not talking about quantization really. Well, quantization is for the operator. The commutation relation phi pi commutation is I h bar, that is a commutation. But okay, you can't say that this is a super quantization. Okay. So, you can say that there is a state in that box. Now, we are Hamiltonian, for that this state is a eigenstate, which of course, it gives you the energy as this one plus half. So, that way it is you are correct, but normally you do not say we are quantizing each of the oscillator, you are doing it all together. No. So, this is a good question. We do not think like that in field theory. Okay, I do not want to. So we do not think like that. Okay, so field theory is not that you are thinking one oscillator with. So if you think like that, then each oscillator will have different level of energy, right? So oscillator 1 with K will have levels like that. K prime will have levels going like that. Okay, then and of course this oscillator can disappear at some point so then this whole energy levels are gone. So do not think in terms of single particle or some of this non destructive particles. You think that we have wave number k, okay, one wave number, it can have some particles. Okay, in fact, then wave number k2, k1, k2, it has some particles. K3, it has some particles. So instead of going for, you can't identify this particle I am doing the quantum mechanics. No, you think of I am doing quantum mechanics of everything with particles being present there. So you have to get rid of this single particle picture for field theory. Particle is not sacrosanct in field theory. The state psi, which has all these particles, that is where we start with. Okay, but the particles can disappear, then what do you do with that? So I wrote that for fields, for classical, what do you mean? No, there is uncertainty relation. So that half came from AK dagger is not AK prime is not commuting. That half, in fact, exactly same. No, so this was 1 h bar, well, omega k. Delta k minus k prime. In fact, I think there is no omega k. This was, well, the prefactors depends on the normalization. This is not 0, and the half for single oscillator in particle quantum mechanics comes because of this relation. But there k was not there. No k, there is no k prime. The single oscillator. Here we have k now. For every oscillator, we have this AK and AK dagger do not commute, and that half is coming precisely from this relation. It is purely quantum. It is not classical. No, you don't say it is property of the operator. No, state has nothing to do with it. This property of the oscillator, like two matrices, either they commute or they do not commute. It has nothing to do with which vector is going to act on. Well, no, it's a deep question and it's an interesting question. So, fractal space is okay. So, everybody knows what fractal is somewhat. So, one example of fractal is that we have triangle, okay, one triangle, in between we remove 1/4 of the triangle, remove this, okay. So, we get out of 4 triangles we get 3. Now, there are 3 triangles, you do the same thing to these guys. Now, you have 9 triangles and keep doing it. So, this is a fractal object and the amount of space is less than 2, because it is not, there are a lot of holes. So, it has a fractal dimension, I think log 4 by log 3 or something of that sort. Okay. Now, it is possible to construct some, well, field theory will not have, we can't deal with this discontinuity and so on, but people construct fields by, so in 2D, so let us say we have a box, finite box. So, we will have number of modes, let us keep it finite, nx into ny, number of Fourier modes I keep it finite, okay, let us say some cutoff. So, I say along x direction there is nx modes and y direction ny modes. If you want, you can keep it infinite, no problem, but now we can make a scheme where you can cut down third wave number every time. So, just think of 1D, well instead of 2D you can just think of 1D, you have 1D line. Now, in Fourier space we will have k equal to 0, 1, 2, 3, 4 like that, right. So, say well I will remove k equal to 1, k equal to 5, k equal to 9 and I can remove that. So, that is analogous to what is done here. Fourier space also you can remove wave numbers at different scales, okay. But quantizing and all that, we will come to non-integer dimensions later. It is possible to do field theory in higher dimensions and the D is there, okay, and it has a very important role. You might have heard that in a 4 space dimension, the fluctuations are Gaussian. Like I heard of this line statement or no? Okay, we will come to that. It turns out in 4 dimensions physics is simpler compared to 3 dimensions. Okay, so we will do that later. So, dimension of space will play a role. Okay, anything else? Okay, so I think let us do one more simple slide and then we will break for today. If I exceed 5 minutes, okay, no, nobody has a class. Okay. So, let us finish this slide, otherwise it will be, it is a deeper slide, I may redo some of it, but let us start it. Okay. So, we did work with the basically field which was oscillating field, which we mapped it to many oscillators, okay, and that had a nice set of properties, but that is unique to that field. The same quantization does not work for all fields, okay. So, depending on Lagrangian we will have to create ways to quantize it or create ways to deal with multi-particle field theory, okay. So, QED has a different field theory, quantum chromodynamics a different field theory, Schrodinger equation a different field theory. So, that is an important point, okay. So, let us do some more, well I am going to now develop the formalism, well some more formalism that was not a general formalism, that was somewhat confined to a bosonic field which was for a scalar particle, it did not have components. So, free particle in many body physics, okay, is more like a condensed matter physics, okay, that is what I am going to talk about right now. So, Schrodinger equation free particle. So, again we will start with simple. So, this is a Lagrangian, no, I wrote before, and we can derive this equation of motion. You can treat this as a classical field, okay. When you quantize this field, then second quantization will occur. For particle wave function, this is classical totally. You can solve this in a computer, size unique at a given time, okay. So, this is not a, this is like string of a motion of a string. Its interpretation leads to quantum mechanics, position is average and so on. We set psi v equal to 0. So, that is a free field, okay. So, free particle I am saying, a free field you may call it. So, my Hamiltonian is this, okay. Now, this is a different Hamiltonian than what we had in the previous set of slides, okay. So, total Hamiltonian will be integral, okay. So, this is integral and Green's function will be this, okay. This I derived it, I mean you can just this I omega coming from here and this is that v is 0, okay. So, we keep v equal to 0, non interacting, okay. Now, so this we had done before, at least this part. So, this is in real space, now we can do it in Fourier space. Now, some of it you should know it by heart, how to derive that. So, this Laplace grad phi squared will give us k squared, no. So, this k squared is here, this phi squared will give you phi k dagger phi k operators, and this 1 by 2 m is here and some more all k's. Now, there is no momentum here by the way, see this pi is gone, we just have phi. So, Here I do not need to deal with momentum operator. In fact, we know momentum is grad phi. Okay. So this, you see, this whole structure of Hamiltonian is different and quantization is different. Okay. So this, I think you should keep this in mind. Now this is my Hamiltonian, and I will try to quantize it and work with it. So it is not going one by one. Okay. So indistinguishable particles, this one is the most important. Now this is a very important slide. Okay, you should pay attention to this one. So in classical physics, we assume the particles to be distinguishable, right? They may be particle of identical mass, identical looking particles, but since the trajectory of the particle is, we can determine it from the initial condition, we can follow it, and so you can say this particle is basically the left particle and that particle is the right particle. Okay. So this is classical physics. In quantum physics, of course, trajectories are not defined. Okay. So then there is no way to say this particle A, particle B. Particle A is following this trajectory, particle B is following the trajectory. So remember, I had said we have a box and I shoot two particles. That is a 2, 3, 1 particle. So let us think of shooting two particles A and B, and something will come out. Imagine the two particles come out. So I send in 2 electrons and 2 electrons come out. Imagine that it was really, well, I mean, think of classical physics where, well, not classical, very simple interaction, not field theory interaction. There is a potential scatterer, there is a big charge particle sitting there and we send like that. But I just shot it, but I do not know what happens inside. But when it comes out, can we say the left guy is A and the right guy is B? You cannot, right? Quantum mechanics does not allow us to say this could be A or B, or this could be B and this could be A. Okay. In field theory, it becomes even more apparent that okay, there is a big thing in between. We do not even know it is the same particle which was sent in which is coming out. It could be very different particle. It could be electrons coming out, 2 sent in, 2 coming out, but it could be I mean, there is no way to say that was the same electron which was sent in. Okay. So these are indistinguishable particles. Okay. So that means we can create particle, well, so this is for scattering. You can think of scenario where I create two particles. Now we already are familiar with creation operators, no? So imagine that in the vacuum, this state 0, vacuum state, I create two particles, particle 1 and particle 2, same 2 electrons, okay, 2 electrons. I create label 1 and label 2, but label 1 was before and label 2 was later, before, later. Well, before, later also becomes a problem sometimes, but order in which I do it, or you can do 2 first and 1 later. It turns out there is no way you can distinguish. Okay. So this is inherent in the field theory that I create this 2 particles, first P2. So we go from the right to left, no, operator will act on a state psi. So I create P2 first and P1 later, or P1 first and P2 later. These are creation operators. So these two operators will do the same thing on state. So this acting on psi will give you new state psi prime or phi. Well, now this phi state has two additional particles, right? Now this acting on psi will also give phi, or it could give a minus phi, because we do not worry about the sign. What we measure is the probabilities. So sign is not important. Of course, you may say, well, it could be some arbitrary phase, but that is not considered. It is considered either plus or minus. So these two operators, when you commute it, when you change the order, this prefactor can be either 1 or minus 1. Okay, that is only allowed. There are of course people are talking about more complicated stuff, but we are not going to get into anyons and so on. This connected to this, but we will assume either plus 1 or minus 1. So, plus 1 is called bosons. When you commute this two creation operators. So, for bosons these creation operators will commute. In fact, I showed you, right, the creation operator is commuted, but what if they do not commute and get a minus sign? This is minus sign, okay, it did not commute. There is a possibility in nature that it can come with a minus sign, and that is fermion. Okay. This is a simple formulation to create both this set of particles, and I think maybe I should stop here and then we can work out. So, bosons I kind of done it right now, okay, I will just recap it and in the next lecture, but fermion we can derive from this simple postulate that the number of particles in a given state can be either 0 or 1, can't be 2 particles. Okay. So, this is just a simple framework we adopt. Okay. So, these operators are very important, okay, and once you set the rules for the operators, everything follows. So, I think it is better to stop right now, and I think we will do things carefully, and we do not do rush. Okay. In quantum mechanics, well, I made life simple here, okay, that I put some simple one scattered. In general, this particle accelerator, or in condensed matter physics too, if you send something here, what comes out is very different. You send 2 electrons and you get all these Higgs particle and some quarks. Well, quarks do not come out, but the just bunch of particles come out. So, here in quantum mechanics we do not know what is inside. If fully you can make predictions and we can make some guesses. Okay. So, we will calculate some of this stuff and I will show you how this scattering is calculated. This Feynman scattering, well, basically Coulomb scattering, you know, no? I mean, one particle goes and there is a Coulomb particle and this scatters. You can do similar calculations for quantum mechanics too, but then it is not in terms of trajectories, but in terms of operators, which I will not do in this course, but it is done with full operators and their virtual particles and all that will come. So, but you basically you are trying to compute from the Green's function plays a big role, and you are trying to get some properties what is there inside, but this state psi or vacuum you do not have much control over that. You can make, okay, this is what, so we can say when I send something this much change will happen, that is a law, but you can't say what is there inside, that is not well, many times not allowed to ask. You can say that, well, yeah, if something goes through it comes out, this will be the change, that is a law. Okay. Yeah. Okay. So, we will stop now. Yeah.